Okay, hi. So I want to continue on from what we did on Wednesday, which was looking at the let's see, this will go there, kind of correlations or how what happens when you start packing uh, polymers together. So we talked a little bit about this. So we have like this would be like a fractal, like a dust particle. So it doesn't have a persistence. It's got some kind of objects that collect together and make a kind of a dust bunny. And so you have that that article is a fractal, so it's got a fractal dimension. So you have a weak. So if you look at this log scattering divided by concentration, this log Q, you have this power law region that reflects the dimension of that. Then you have a Grignard region that gives you the size scale, kind of the overall size of the thing. And then as you go out, you eventually get to one of these, and then it's got a sharp surface. So it has forward scattering, the reflection scattering. So the scattering off the surface gives a steep decay. And that knee here is the size of one of these primary particles that make up the structure. So it'd be like a Kuhn unit in a polymer making up the chain. If you increase the concentration, they start to interact with each other, and then you see this screening of the scattering because you can't see one of these anymore. The largest thing you can see is the whole, and that's the correlation distance between these objects. And as you increase the concentration more and more, you screen more and more, so the correlation hole gets smaller, so that correlation size moves over to the right. It's actually 1 over that size for Q. So the size is getting smaller, but the Q is getting larger. And then finally, you reach just one particle, and then that's kind of the end of the story with it. They're touching. It's like close packed. So at that point, so you can't get any denser than that. So the idea is like you can say one sheep, you can see it, but when they're in a flock, you can't really identify the one sheep. So he's trying to count the sheep, and you can't do it when they're crowded, right? So you lose that. What you gain is this correlation distance, and also the I naught here tells you the second virial coefficient. 1 over the second virial coefficient is I naught. So basically, it's a measure of the thermodynamics of how the system mixes, right? So this is called the mean field. So there's two, mean field where it's kind of a random system, and then you can have specific interactions. You have correlations, and you set up kind of a organized structure with a preferred separation distance. So the random system here is actually a picture of the stars. So stars are randomly arranged. So it's kind of showing what a random distribution looks like. There's some clustering, there's some voids. So that would be a random system. If it's completely filled in space, it's not random. So you might make it random and you show dot, 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 dot. Because you did it in a regular pattern, and because it fills space, it's not random. Right? So these mean field interactions, we're looking for this kind of random situation. So anyway, that's the scheme. So if you increase concentration, you get this diminishing, and then at different temperatures, you also get a change in that screening. Okay, so the screening is related to the temperature and to the concentration. So you have chi would be 1 over T, and this concentration is a concentration. Right, so this prefactor is more or less what you're measuring when you kind of watch that decay with as you increase the concentration. All right, so it's temperature and concentration dependent, and then so so let's see. So how did this get to here? Okay, ordered these wrong. So basically, what's happening in the structure in that is that the chains are in a good solvent. So this is a 5/3 power law, 1.67. And then as the screening goes on, they become like a melt, which is Gaussian. So that at the large sizes, they're Gaussian. At the small sizes, they're expanded coil. So if you could see the scattering from one chain, you can't see one chain in this because you can only see the correlation distance. So you can't see this part. But if you could see that part, then you would see this curve. You'd see persistence unit, good solvent, and then it would transition to Gaussian, steeper, and then you'd get the coil size. And so there is a way to get that curve of what one chain in that mesh looks like. You can tag one chain with deuterium, so it kind of paints it red, and then have most of the chains hydrogenous, and then you can look at the one chain. Basically, that one has much more contrast than the others. Then you can observe the scattering just from that tag chain, that system, and then you can get this curve. So this idea that you have a transition in scaling means that this Gaussian walk is actually made up of units. So the subunit of that isn't the persistence unit. Subunit is this good solvent coil unit. This is sub part of the chain. So you've kind of coarse grained the chain. You've rescaled the chain in terms of this good solvent, what's called a blob. So that's called a concentration blob. So you have these good solvent subchain units that make a random walk. So you get Gaussian here. So you get these two scaling regimes. When it's a mesh and there's no tag chain, then that's invisible because that's just a uniform medium, just like a glass of water or something. So it doesn't have structure to it that you can observe because the structure is screened. So the structure becomes invisible like this, like the large scale structure disappears. But if one of these chains was painted red, then you would be able to identify it, and then you could observe what's going on with that. Right. So the way to describe this this scattering is to include the chi parameter. This would be called a random phase approximation equation. So it's the inverse of the intensity goes with the dilute intensity and then minus this two chi times concentration. So at a high concentration, this number is large, but so when the intensity at high Q is small, so 1 over that intensity is large. So its size is smaller than the correlation length. This intensity is small, 1 over it's large. It's larger than this interaction thing, right? So your intensity here is dominated at high Q by the dilute structure. And then as you go to lower Q, this intensity gets larger. So 1 over that intensity gets smaller. It gets smaller than this interaction parameter times concentration. And then you just get this thing dominates the intensity that you see. So this thing would be the flat, right? So this flat thing that you see if you go to low enough Q is going to be the chi parameter times the concentration, 2 times chi times the concentration. So that's how the RPA function works. And also, if you have a mixture of two polymers, A and B, and then you want to know what the scattering is going to be, you use this same kind of inverse sum. So I wanted to kind of briefly go through this. So this is called a random phase approximation, this kind of inverse sum and with the 2 chi thing like this. So susceptibility is proportional to the scattering. So it's 1 over the scattering. It's 1 over the component 1 scattering, 1 over component 2 scattering, and then 2 chi component to that. Okay, so anyway, so to get that equation, right? So the best place so the derivation of that equation is complicated, but a good place to get it is in the Strobel book, which is on the web page. And I don't link it here, but see if I can get that. So this is the Strobel book. This is page 4. I think it starts in 4. It's in the appendix, right? This binary mixture, whatever. So 477. And the book is this, it's on the web page. It's this book, Gerd Strobel Physics of Polymers, right? So 477 is down here somewhere. So it's actually at the absolute end of the book. He puts in an appendix for this RPA equation. It's it's kind of the simplest write-up for this anywhere, right? So de Gennes, who wrote this equation, right, the equation was around, but it hadn't been demonstrated. So the equation, Dick Stein actually had used this equation, this inverse sum equation, and it pretty much falls out of the Zim approach if you look at it the right way. So the equation wasn't really surprised, but the derivation of it was kind of not there. the gens figured out that you could get that equation by going to dielectrics and look at, so by analogy to dielectrics and saying that the scattering um, is related to the susceptibility in dielectrics. So in dielectrics, you have a field that you put on a material and you're looking at the dielectric susceptibility to the field, like how polarized does it get in the field. So you basically took equations that already existed for dielectrics, and then you kind of made that the susceptibility is basically, or the scatterings are related to the fluctuations in the system, and the fluctuations are related to susceptibility times the field. So the field that's put on the material, the susceptibility gives you the fluctuation. Fluctuation squared is the scattering. So that means that the susceptibility and the scattering are related to each other. So if you can solve for the susceptibility, you have the scattering pattern. And in the end, he gets that it's the scattering pattern from a mixture of systems, this inverse sum. So the harmonic sum of the two components went into it, which means the smaller one dominates. Like the smaller one over a small number is a big number. So that means that the small numbers dominate in a mixture of two. So in the paper this week, he doesn't do this. He just sums the two scattering from a small chain and a large chain, and he says he gets the total scattering from that sum. But that isn't right. What you should do is do 1 over, and that would have a much more dramatic impact on the sum of the two, because the small chains would actually dominate the whole system, right? So just summing the two together isn't how these things work, because it's more complicated than that, because they intermesh with each other. Anyway, so that said, I wanted to just quickly so if you want, you can read this, and it's pretty simple. I think once you get over the fact that he's talking about susceptibility and fields, then it's just straightforward what he's doing. So I just wanted to, like in 2 slides, go through the derivation of the RPA equation, because I think it turns out that this is kind of useful to know, because it gives you a different way to, like, you can figure out how things would work in terms of scattering, so in terms of mixing complex systems like 2 polymers. So anyway, so he in that chapter, he explains like why the scattered intensity that you measure is going to be proportional to KT times the susceptibility number. And then what the susceptibility is if you put a field on a system, then there's going to be a fluctuation. The susceptibility decides, so it's a constitutive parameter that decides how the field affects the concentration fluctuation. Concentration fluctuations give rise to scattering, right? So anyway, that's kind of how this goes. So there's a link between dielectrics and scattering as if you put it into this framework. So it's going to say he has a mixture of A and B. So if you take 1B out, if you put 1B in, you have to take 1A out. So the fluctuation of B, so this deviation from the average, has to equal the negative deviation of A, because if you pull this out, that has to come in, right? So he defines just this um, nameless fluctuation, which is the A fluctuation. It's minus the B fluctuation. So you pull the A out, the B has to come in. The reason that the B comes in is because of some kind of field between A and B, like a chi parameter. Somehow it creates an internal field that isn't the applied field. So you apply a field, you get a fluctuation, right? So for us, that's kind of like KT causes fluctuations, but in dielectrics, it's actually a field, an electric field that you put on a sample. It gives a fluctuation of the polarity. Anyway, so it's linking the two things together. It gets a little mishy-mashy, right? But basically, you have the applied field, and then there's this response field that makes the B move. So the A will move to the field because it's polar, and the B isn't polar, so it doesn't move to the field, but it moves because the A moved out of the way. So the B has to come in, right? So this is the internal field. This is the external field. So the A is sensitive to both the internal and the external, because if you move a B, the A has to come in also. So you have the external field, the internal field, and this is the fluctuation, which is the A fluctuation. All right, and then the B fluctuation is a negative of that, and it's going to be just due to the internal field, the thing that it has to replace A. Right. So if you combine these two, then you can solve, because you have two equations, and that you can solve for the internal field, which is the thing you don't know. So the internal field is going to be the scattering from A. If it was a pure A component, the divided by the scattering from pure A, pure B summed, then times the external field. So as nothing happens unless you have an external field. Once you have an external field, you get this internal field. They're proportional to each other, right? So, right, so you can get that, and then you can solve. You can plug this back into that, and then you can solve for the fluctuation, and you find out you get this equation for the fluctuation and the field. Then you can plug that back into your equation for A0 up here. So you have phi k you can put here. You have A0k, and this has a phi k. So you can just solve for A0k in terms of these guys, which are the independent scattering. So each of these is going to be a Debye scattering function for each of the separate polymer coils that are mixed. You have a mixture of two polymers. And that gives you directly, when you rearrange, you take this and combine it with that, you get this equation for the observed field as the Debye function for the A and Debye function for the B, and it's a harmonic sum. So the small one dominates, right? That's how you decide how a mishmash of things together would give rise to what the scattering function would look if you have this interpenetrated structure. But this doesn't have a chi parameter. So that's what part B of this thing. So part A gives you that with no chi parameter 0, so it's called athermal. If it's not athermal, so then you have a chi parameter, so the field, and then the chi adds to the field. So it's like a interaction potential that adds to the field. So this is your original equation that you had was just the field. So that fluctuations, the susceptibility times the field. You have the fluctuation susceptibility times the field plus this chi parameter, and the chi parameter has KT in it. And so chi is 1 over KT. So this has no KT in the end. So it's 2 times the enthalpy of interaction. It's a strictly enthalpic term, right? So anyway, so once you have that, so then you just rearrange this and solve for, let's see, what do? You rearrange, let's see, phi k is alpha k 0 over, yeah, you rearrange this thing, because this has a phi k here and a phi k there. So you club up all the phi k's, and you divide and rearrange it until you get just what one of these phi k's is. So you have phi k minus chi prime, 1 minus chi prime on this side, 1 minus chi prime alpha k0. Then you have alpha k0 here, and then it's times this guy. So that's just rearranging this, gives you an expression for phi k. And then alpha k is going to be alpha k times the field gives you the fluctuation. So you can say alpha k is phi k over that. So alpha k equals this mess. And alpha k0 is our sum up here, right? So you can plug that thing back in here, and then you can get the full RPA with an enthalpic chi, which is the thing that we kind of used in the. So if you just have a solvent, if you have to have a polymer and solvent, you just have phi AA, then minus 2 chi. If you have two polymers mixed, it's a harmonic sum of those. So for the polymer and solvent, that's the one we had. Oh, somewhere here I showed that. Anyway, the polymer and solvent is here someplace. Here. So this is the polymer and solvent. It's the RPA. So it's like 1 over the dilute and then the chi parameter, and that gives you the sum thing. So that's the same as this equation. The BB doesn't exist. Right. So it's a little involved. It's kind of simple and it's kind of involved. I mean, if you look at the actual derivation papers, it's really complicated. And if you look at Strobel's appendix, it's really simple, actually. I mean, this is pretty simple. It's just algebra, moving some things around. You can get that equation, which this is one of the seminal equations for polymers. Like, how do you understand what scattering you would get if you had two polymers mixed together? Right, this answers the question. So I think this was mentioned in Degen's Nobel Prize, this equation, even though, again, like Stein had already published this equation, but he published it as an empirical equation. He hadn't derived it, right? So anyway, so that's that business. I went through that. The correlation part gets to be pretty messy, and in the past, I've gone through it in some detail, and I'm not sure how valuable that is. But basically, you're going to use the Ornstein-Zernike approach to talk about the correlated things like the woven fabrics. And that's going to rely on this idea that you have so you're going to have you want to know what the combination of so you have specific interactions that are local, and then you have so the total correlation is this H of R, which is related to the correlation function. And then there's indirect correlation. So when you have two things correlated, then they couple together with other things in the system. So there's a C of R, which is the indirect correlations. So you have two things. In order to get C of R, in order to get the correlation, you need to know what this indirect correlation is. It ends up being a convolution of the two, and then you have to have a closure relationship to solve it. So it's complicated. Basically, it's pretty complicated. It gets to be like a total mess. So anyway, I'm not going to really go through that, I guess. That's how this looks. This is another equation due to Debye that's a scattering function for spheres. And if this function for spheres, if you go to low Q, so this also has limits. So if you go to low Q, you can expand the sine and cosine terms like that, and you get Gaugnier's law. If you go to high Q, the sine Q averages to 0 because plus and minus are opposite sign. And then the cosine goes to 1/3, and you have QR over QR cubed. So you end up with QR squared. Squared gives you Q to the -4, which is Broad's law, like for reflection from a surface of a sphere. So that Debye came up with that equation also. So anyway, this equation is kind of straightforward. By doing just the integral of a correlation function for a sphere, you get that answer. So it isn't as complicated as the Polymer scattering function. Let's see. So if you see a peak, you have specific interactions, and you're in for all kinds of mess. And if you don't see a peak, you're in much better shape because you can just use the RPA equation to describe the scattering. And that's pretty well founded at this point. So that's kind of it for that part. So I'm gonna end that thing. It says go to second half. So I'm gonna dump that. And then this part is about not scattering, but other measure of size, which is a hydrodynamic radius. We had to plot RG, which you get from scattering or you can get from simulation, then RH, which you can only get from experiment. Like it isn't really easy to calculate RH. Nonetheless, the thing that people use is this Kirkwood-Reisman equation or theory to calculate this hydrodynamic radius. So it's possible to calculate it. So you can see if you look at when we did the calculation for radius of gyration, it ends up as a sum of r's, right? And then this is the sum of inverse r's because the diffusion coefficient, which is the dynamic thing it measures, 1/r, right? So because the dynamics are decided by 1/r, this ends up being a double sum, like this double sum for radius of gyration, but of the inverse sum, which is a harmonic mean, meaning again that the small things are more important than the big things, right? So anyway, if you calculate it this way, so what's going on is you have the polymer chain and you're calculating for each of the little monomers in the polymer chain as if they were independently contributing to the diffusion coefficient. So that means that there's no solvent involved. That means this is a fully draining chain. So this calculation is for a chain that has no solvent or no hydrodynamic interaction. That's what they call it. So if you have full hydrodynamic interactions, then this RH is just like the end-to-end distance. Let's see, let's go here. So you have so you could think like this Kirkwood-Reisman thing. You have all the units, they're labeled I, you go across them, and they're also labeled J, the next sum, right? First sum's I, second sum's J. And you do the double sum over that. And then you just see kind of what the drag is on that. What's the diffusion coefficient going to be, like the friction factor for that whole thing. On the other hand, so that's draining, right? On the other hand, and it's called hydrodynamic, there's no hydrodynamic interaction. On the other hand, you could have under the limit would be like all the solvents perfectly trapped in that, and your RH equals the end-to-end distance, right? The solvent's totally trapped. It's a sphere of solvent. And when you pull it along, it's the friction factor, the sphere's friction factor times the viscosity of the system, right? So that's a much larger RH than if you do the Kirkwood-Reisman calculation. So you have two limits like draining, non-draining. And somewhere in between is where the situation is. So to calculate that, you need to think about this hydrodynamic interactions within the coil, which is messy. And you probably don't want to do that. And you probably can't actually do it, right? So anyway, so that's kind of the idea of this calculation of the hydrodynamic radius isn't that simple, right? I mean, there's things involved, some of which you don't know the answer to. But if you assume fully draining, then you can do this, right? So that's possible. So depending on what the object is, if it's a sphere, then if you take, so you can take the RG, we can calculate, we have an equation, we get RG. It doesn't have anything to do with hydrodynamic interaction, it's a structure, right? So an RH has these other features. So if you have a sphere, RG of RH is 0.774, right? And then if you have a coil, then it's going to be larger than one. So kind of one is the cutoff. If it's less than one, you have a solid 3D object. Above one, that ratio of RG to RH, then you have some kind of a fractal dust bunny branched or linear structure, right? Theta or expanded. The more open it is, the bigger the ratio, right? So that's kind of how this thing is going to be used. Like people will measure RG and RH, take the ratio, and then try to say what it is they're looking at to tell like how, if it's a collapsed chain or what. Like we did that in the in looking at the coil transition that see, did I actually close that thing out? Yes. But I can open recent this thing. So we have that over here. It's a lot of slides. When we did the coil collapse thing. Oops, it's actually pretty far back. Down memory lane. It's right after this. Right, these guys, what these guys did was look at RG by RH, and then if it's above one, that's a coil. If it's below one, that's a 3D, so it's collapsed. So this is expanded, that's collapsed. That's a first order transition. Right, and the fact that it goes through this dip and up is because they're going through reorganization. So I think they're going from something like molten globule to like native state type thing. So it's slightly more compact, then becomes less or something. I mean, it's basically they're using this RG by RH to say exactly what I just said, that it's like a measure of what the thing is. So that's kind of the scheme. So there's two main ways to get RH. One is you can get it from the intrinsic viscosity. So intrinsic viscosity is 1 over the overlap concentration. So you have the mass of the chain, and then the hydrodynamic radius of the chain cubed times 4/3 pi gives you the volume. So mass by volume gives you the overlap concentration. So 1 over that's the intrinsic viscosity. Right. I'll show you a little bit about how people have gone about measuring that. And the other way to get it is through dynamic light scattering, where you actually measure the diffusion coefficient. So I'll go through that too. And there's also other kinds of dynamic scattering like X-ray and neutron kind of dynamic scattering, similar to light scattering, where you can get this diffusion coefficient and kind of 1 over that gives you the hydrodynamic radius. Right, that's the Stokes-Einstein equation that we went through before. So basically so I'll go through these two analytic techniques of measuring hydrodynamic radius. That's our goal here. Let's see. So, all right, that's good. So this is Kirkwood's grave. It's kind of a joke. So it's in New Haven, Connecticut, Yale, right? So this guy, Kirkwood, never won the Nobel Prize, but he thought he should have. And on his grave, he like lists all the prizes that he won. Da, 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 da. And then Onsager, so he was 59 and they overlapped 07, 03, so they kind of overlapped. Onsager lived longer. So anyway, so Onsager won the Nobel Prize. So he died after 91, and this is 59. So he basically said like he just didn't put anything on his gravestone. He just put Nobel laureate because it's like he's right next to Kirkwood, right? So it's kind of a joke. It's like the last laugh. Anyway, this is just showing like for different shaped objects, people have calculated what this RG to RH ratio would be for this. This is in this paper by Stockmeyer, who's a guy from all these people are kind of famous in the polymer physics, kind of early 60s, 70s time period. Stockmeyer was at Dartmouth. I'm not sure where these other. Burchard's a famous guy. Schmidt must have been famous too. Anyway, so the viscosity. So if you measure what is viscosity, so you can measure it in this capillary viscometer, right? So there's a capillary between B and down here. There's a very thin tube, right? And then you put a fluid in. It happens to be a pink fluid, so you can see it. And you would pump it with a bulb over here until it went above A, and then let it flow down. And then once it crosses A, then you start your timer. So you have a stopwatch in your hand. And let it go through here. So it's flowing right through this capillary. And then once it gets to B, you stop the stop timer. So it's following Poiseuille's law, so that Q is the volume per time. So if you take so every other thing in here, the pressure drop is atmospheric gravitational pressure. L is the length of the capillary. Then you have the viscosity. So viscosity goes with 1 over Q. 1 over Q is the time that it takes, the time that you got. So the higher the time and the higher the viscosity. They're proportional to each other by Poiseuille's law. As long as you have a laminar flow, which you have in this thing. So anyway, so it means you have low viscosity, right? So basically that works. You can, so if you want to say, use that machine to get the intrinsic viscosity. So you do that with the solvent, that would give you the 0 time. So you just use time. Then you do it with the solution, you get a time, and take the ratio of those two, subtract 1, divide by the concentration, you get the intrinsic. And so that's kind of how you do this measurement. You don't actually measure the viscosity because you don't know. I guess you know everything in here, so you could get the viscosity if you wanted to, but it's easier just to get the time and then just get the intrinsic because that's the units of concentration, and you know the concentration, right? So units of inverse concentration. So that's basically how that guy works. This is a cup and bob viscometer, so the cup is missing. And usually the cup is heat controlled, so it's got a water bath going to it because the viscosity is going to be dependent on the temperature by the Arrhenius function, right? That we looked at before, like this. So basically, there's a strong temperature dependence to the viscosity. This is showing with temperature what happens to the viscosity. So you get a steep decay, right? It follows kind of an Arrhenius dependence. But so anyway, this operation for the viscosity measurement, so you put some kind of shear. So usually you talk about this laminar flow setup. So you put a shear on the top. So you apply a force like on a deck of cards and it deforms the fluid, right? And the area that you apply the force to is the normal to that area is normal to this. So it's kind of a 1-2 or XY stress that you're putting on it, this tau, right? The force and the area, the normal to the area and the force are orthogonal to each other, right? So that means this is like an XY shear. It's a shear stress. And then there's a change in the distance. So there's a distance change divided by the y. So this is also xy. So that's a shear strain, right? So you have a shear strain. And the shear strain you're looking at is actually a velocity. So it's the distance per time divided by the distance dropping. So it's a strain rate, or it's a velocity gradient. Now it's a velocity as a slope, where it's highest at the top and stopped at the bottom. So it's a linear slope for laminar flow. And then you get the rate of strain or the velocity gradient. And they're related to each other by a constituent parameter, the viscosity. right? So there, it's all done in shear, 1, 2, 1, 2, or x, y, x, y, and then this is the constitutive parameter that relates those things to. So that'd be a Newtonian fluid. In other words, the viscosity doesn't depend on the shear rate. In fact, the viscosity does depend on the shear rate, right? So you have to kind of be careful. Let's see. It's here. So it's concentration. Here's shear rate up here. So you have, this is for solution viscosity, and you can see that the capillary viscometer for this system, which is xanthan gum, 0.1 mole per liter sodium chloride solution. So it's salted out probably. And then it shows shear thinning even for the capillary viscometer, meaning that you have to use some other lower shear rate setup like a Zim-Carruthers viscometer, which is basically essentially this cup and bob viscometer. So generally people just use this, but in some cases it could be a problem. Like xanthan gum has a high viscosity, and in that case, you probably need to go to a cup and bob viscometer. We can change this setup so it's not so the bob is small, so you get a lower drag coefficient, kind of get it to a lower shear rate. And then you could measure this at different speeds and see if you get a decay in the viscosity at higher shear, then you know you have to go to a lower shear rate. Right. So with this setup, you can test the shear rate and viscosity dependence and see how that's going to work. Let's see. I know what the problem here is. Let's see. This is the problem. Let's see. Yeah, that should solve that. So, all right. So let's see. So that's kind of the setup for a viscometry measurement. Then all right. So then so a while back we mentioned that this equation for the equation for the intrinsic viscosity, like this, what equation? This equation for intrinsic viscosity is basically just a displacement law. So you can kind of look at that. We went through this, so you can displace the fluid by whatever it is you're putting in, and then you would get a change in the gap distance. And then if it was you could express that as an exponential or as a small number as a 1 minus the argument. And then if you do it as an exponential, then you can kind of figure out that that's a displacement law. I think that's kind of the gist of what we did before. We've already done that. So basically this equation was due to Einstein. This is the Einstein viscosity equation, but he said that this was the equation that he was like embarrassed that he had come up with because it's such a simple equation, I think. But anyway, so that said, so then we have all these different viscosities. So I kind of went through these already, but so if you just take the solution viscosity and then you measure it against concentration, you'll find out that it's got a steep dependence because it's entangled at moderate concentrations above like 5%. It's going to be entangled. You're just going to see a power law of 3 or 3.2. And then it'll go to 0 because you've reached the solvent viscosity. So that's kind of a useless curve. In order to see the details where it's 0, you need to subtract off the solvent. So if you subtract off the solvent, then you have well, if you subtract the solvent and then divide by the solvent, you have specific viscosity, or you could have just the relative viscosity would be the viscosity divided by the solvent. So that relative viscosity is kind of useless. The specific is the part just viscosity minus solvent isn't really a name, I guess. So basically, but you would see this power 1, power 3. If you divide by the solvent viscosity, then you get this magic thing that around value of 1, you're going to get the transition. So about when the viscosity is twice the solvent viscosity, that's where you see the transition to entanglement for whatever reason. And then if you extrapolate this down to 0,
So you extrapolate to zero concentration, then you find that you have the intrinsic viscosity. So when this guy goes to extrapolating down, so this minus that divided by the solvent and then divided by concentration will give you the intrinsic viscosity at the limit of it going to zero. So the zero intercept is where you want to get the intrinsic viscosity from. Okay, so basically you need that kind of curve and you need to find the power one region to find the intrinsic viscosity. More or less, you can do it graphically like that. So that's an expression for this intrinsic viscosity. So limit as concentration goes to zero of the specific viscosity divided by concentration. So or the reduced. So this would be the reduced. So to limit its concentration to zero, the reduced viscosity. So you have reduced, relative, and specific. It's like too many, right? So but basically that's how it goes. And then this is going to be 1 over the overlap concentration. Anyway, so if that's not complicated enough, then people, because there's problems with this. So the problems are it deviates, right? So you have the viscosity, the specific viscosities. This is a reduced when you divide by concentration. You want the limit when it goes to zero, but it's not linear, right? So this it's not perfectly linear. This is acetyl starch, so some kind of polyelectrolyte, right? So it's not going linear. So what do you do with it? Well, you make it into a power series to deal with it. And you have some arbitrary constants that deal with that. So that's the first thing you would do is like a Taylor series to fit the data, and then you can extrapolate to zero to get the intrinsic. That's kind of like, so this is from, there's a bunch of books written on this kind of subject. Okay, so anyway, so that doesn't look very neat. So people have come up with, well, this power series looks like you could, if the constants were all this, or followed the 1 over 2, 1 over 3 factorial, then it would be like an exponential. So you could just say, well, that thing's really an exponential of this some constant times concentration as an approximation. So that's the Martin equation, right? And then so you have kind of the lead intrinsic, and then the rest of the power series terms you just bury in some arbitrary exponential function, right? So that's pretty common to do that type thing. And then the other thing is, oh, let's take the first two terms. It's like take the two squared terms, and that's good enough. That's the Huggins equation. And then you can do other things, right? So this is similar to the Huggins. It's an exponential expansion, the Kramer equation. So there's various equations to kind of describe this slight deviation that can't be fit with a straight line. Right, so that you might see those things floating around. Then there's this issue that, well, I found the intrinsic viscosity and went over that's the overlap concentration. I'm plotting against overlap concentration. I'm plotting against concentration, so I can put overlap concentration on that. And then I have kind of the cutoff where this thing should go to power 3, say if the overlap concentration is the same as the entanglement concentration, then I have this cutoff point that I can map on the same plot of this. So that's possible to do. I mean, these are all things that people have done and studied, right? So then there's solvent quality effects that come into play with the intrinsic viscosity. So the issue is the thing starts to look a lot like the viral expansion, like a thermodynamic equation. But then you have to remember this is dynamics, it's not thermodynamics, right? So this is viscosity, it's not measuring enthalpy. So basically, the equations start to look a lot like equations for the viral expansion, but it isn't. So you can say like some question of solvent quality and viscosity, it's not the same kind of solvent quality with the chi parameter. I mean, there's a difference between dynamics and thermodynamics, right? So anyway, so nonetheless, there are differences when you put polyacrylamide, this polymer, into water, foramide, and glycol, right? Depending on the interactions, you get a different intrinsic viscosity and a different kind of slope for these curves and different deviations from it, so that which equation you would use to fit it. So people have pretty much studied this like crazy, right? So So this is looking at different molecular weight, kind of molecular weight dependence. So molecular weight dependence, the Markowitz coefficient is what people have done, right? So let's see. So we can just say right, and this guy, that guy is good there. All right, so you can say that the intrinsic viscosity is 1 over C star. That's going to be N over volume, right? Volume is R cubed over N, and R to the dF equals N. That's the fractal thing, right? And we know dF equals 2 is theta, dF equals 5/3 is good solvent, dF equals 1 is persistent, dF equals 3 is some 3D thing, right? So we have kind of those cases for this dF, and then we can plug it right in here. So it's going to be like N by, so R equals N by dF, 1 by dF. So you're going to have N to the 1 by dF minus 3 by dF minus 1. Right, so you can say the intrinsic viscosity goes with some constant times the molecular weight to the A, and A equals 3 by dF minus 1. Right, so this is called the Markowitz equation, or MAG. And then say dF is 1, say we have a rod. Well, then you have 3 minus 1, you have 2. So the A values here could be put into a table, whatever, too many things, but so you'd have 2 for a rod. So that's easy. And then if dF is 2, you have 3/2 minus 2/2 is 1/2. So for theta, it's 1/2. If you have a good solvent, so you have 3/5, you have 5/3. So 3 times 3 is 9/5, minus 5/5 is 4/5, and times 2 is 8/10, so 0.8 for a good solvent. And if it's 3D, this thing is 0. Like 3, that would be 1 minus 1, 0. Right, so you don't have a molecular weight dependence, the intrinsic viscosity for 3D objects. Yes, so it's basically these are kind of the things you look for. You have intrinsic viscosity versus molecular weight. Then you want to kind of look at the dependence as a function of molecular weight in terms of the Markowitz equation. And you can kind of calculate what so you don't get exactly a half 0.8. You get things, and you do get 1, you do get 2 sometimes for like tobacco mosaic virus or something. Anyway, so for 3D objects, the thing doesn't depend. So you get the 0 dependence, doesn't depend on molecular weight. So the solution to it is this equation. So you have intrinsic viscosity is 2.5, and it's a fixed value. It doesn't depend on the molecular weight. It's just a volume fraction of the things, the 3D things that you put in. So that's actually the Einstein equation, this thing. The solution is a solvent times 1 plus 2.5 times the volume fraction. And that's like a general rule that people take for not just viscosity, but you'll see like for a composite, and then you put particles into a composite, the modulus is going to be the modulus of the polymer times 1 plus 2.5 times the volume fraction of the things you put in. Right. So it's basically this thing is used for modulus and viscosity and probably other things. So they kind of just say whatever parameter they want, 1 plus 2.5 times volume fraction, because if it's a 3D object. Then the others are by this 3 by dF minus 1 thing. So there's that business. Then and then the size that you get from this is the hydrodynamic size. So it depends. It's either the non-draining model, which would be the Zim model, spherical. So this is basically non-draining because we're just saying that we're taking the mass per volume as the size of the thing. Right? If it's draining, then you wouldn't get this dependence. Right? So this is called the Zim model when you assume that it's non-draining sphere. this, right? So anyway, so there's a Zim model, which is a non-draining, and they have a draining model, which is kind of the Kirkwood-Reisman model for the chain. What else? Temperature effect we talked about already. Let's see. So let's see. Hold on a second here. 45. So we got just a few more minutes here, I think. So we already went through the temperature. So if you start with an Arrhenius function for the temperature, which is general rule for everything, and then you can, if for polymers, they talk about the WLF equation, which is this, which doesn't seem very decipherable. But if you think about this energy, so if you think about the energy is actually an enthalpy minus entropy times temperature. And then if you include a Vogel temperature here, so like in other words, at the glass transition, thing stops, you need some other temperature other than absolute zero to ground this in. Then you have a 3-parameter equation, enthalpy, entropy, and this Vogel temperature, which is 3 parameters here, this TR, which looks a lot like the Vogel temperature, C1 and C2. If you equate those two together, you find out that TV, this T Vogel, is C2 minus TR. And then this SA is 2.3, because this is log base 10, this is exponential, like log base 2.7, whatever. So anyway, you end up with 2.3 C1 for SA. So C1 is basically the entropy. And then HA is C1 times TR. So it's kind of, that's basically what you end up with. So you can translate directly WLF to this kind of more understandable format, which would have values that meant something. So this WLF is kind of a goofy way to do this. Like you should do it this way. But this is something I did. This isn't like published or anything, but basically this is how you should probably be doing this stuff, not like that. Anyway, so and it also would give you the real Vogel temperature, which is something that people talk about in other areas other than polymers instead of this TR number, which isn't right. So TV is not TR. It's actually C2 minus TR. So anyway, so this is a better way to do it, I think, but it isn't. No one does this, but basically, I think it would be better. I mean, the units of these would be like energy and then energy by temperature. So like enthalpy and entropy, and then you could start talking about what's going on in the system rather than just having C1, C2 that have no meaning. Right? So anyway, so let's see. So I think I'm out of time. That's 44. I think I'm out of time. So the other stuff is just probably we don't care that much about. This guy Simha wrote a number of books on the subject. He was in Ohio. He's like a Case Western. He's kind of one of the pioneers of polymers. And a lot of the work he did was on intrinsic viscosity, and most of it had to do with like colloidal things, not just polymers. So like how you write the intrinsic viscosity for prolate and oblate ellipsoids, and then various other shaped objects that could be colloidal particles, like basically tobacco mosaic virus, DNA nanotubes in solution. You want to measure the intrinsic viscosity. How do you get the length of it out of it or something like that? Right. So there's quite a bit to this. And then the shear rate dependence thing I talked about already in branching. So I'll have to just briefly mention branching next time. So I'm going to quit there because I'm out of time. So hopefully that's okay. So we'll start with 22 on Wednesday, I think. So I'm gonna stop this guy. I can figure out how to do that, and then